Hey everybody, I hope you had a great week. Today we're going to be going over some Chapter 12 example problems. And in Chapter 12 we're introduced to the analysis of variance, which is a procedure that is used to test a hypothesis and evaluate mean differences between two or more treatments or populations. An ANOVA can be used with either an independent measures or repeated measures design, and unlike a t-test, can be used for more than two treatment variables or factors. And it also minimizes the risk of type 1 errors. Our first example question compares 3 treatment conditions in an independent measures research study. And we are first asked to compute the sum of squared deviations for the set of 3 treatment means. Since the sum of squared deviations is the sum of x squared minus the sum of x squared divided by n, we first need to find the sum of x and the sum of x squared. We'll add all of our means together and find that the sum of x is 12, and then we'll square each of our scores and come up with a sum of x squared of 62. We'll plug these two values into our sum of squared deviations calculation, where 62 minus 12 squared divided by 3 equals 14. Next, we are asked to multiply n times the sum of squared deviations of the means, which is going to be our n of 10 multiplied by our SS means of 14, which will give us a value of 140. This should be the same answer that we come up with for the sum of squared deviations between treatments. Next, we're asked to find the total t for each sample and the grand total g. Well, the mean times n equals t, so we'll take each mean, multiply it by n, and we'll come up with our t values. Now, we'll also calculate the value of t squared divided by n, because we'll need to use it later. So the value of t1 is 20, and t squared divided by n is 40. Our second mean is going to be 3, and we'll multiply it by its sample number, which is 10, and come up with a t value of 30. We'll also calculate t2 squared divided by n2 to use for a later calculation. Our third mean multiplied by n gives us a value of 70, and our t squared divided by n equals 490. Now, to calculate g, or our grand total, we'll add t1 plus t2 and t3, and we'll come up with a value of 120. Next, we have to calculate the sum of squared deviations between treatments, and we'll use our formula, which is the sum of t squared divided by n minus g squared divided by n. Since we've already calculated t squared divided by n, we can just add up 40 plus 90 plus 490, and then subtract our g value squared divided by capital N. The capital N indicates the total number of scores in the entire study, where the lowercase n is just the number of scores in each treatment. When we finish our calculation, we'll find a sum of squared deviations for between treatments to be 140, which is the same value we came up with earlier when we multiplied the number of scores in each treatment by the sum of squared deviations for the means. Our next example problem provides us with a data table that summarizes the results from an independent measure study comparing 3 treatment conditions, where first we'll calculate the sum of squares within treatments, which is the sum of each treatment's sum of squared deviations. We come up with a value of 16. Next, we'll calculate our sum of squared deviations between treatments, which is slightly more complicated. So first we'll add up all of our t-values squared divided by their respective n values. And then we'll subtract our grand total squared divided by the total number of scores in the entire study. And we'll come up with a value of 30. Now, to find our sum of squared deviations total, we'll take the sum of x squared and subtract our g squared divided by the total number of scores in the entire study, which equals 46. We can check this value by adding the sum of squared deviations within treatments and the sum of squared deviations between treatments, which is our alternative calculation for the SS total. Our degrees of freedom between treatments will be k minus 1, which is the total number of treatments minus 1. In this case, we have 3 treatments, so our degrees of freedom between will be 2. Find our degrees of freedom within treatments is the sum of the degrees of freedom of each treatment. So 5 minus 1 is 4 plus 4 plus 4, which is 12. The degrees of freedom total is the degrees of freedom within plus the degrees of freedom between treatments, which is 14. Next, we'll determine the mean square for between treatments by taking the values that we found earlier of the sum of squared deviations and dividing it by the degrees of freedom. In this case, we get a value of 15. Our mean square within treatments will be our sum of squared deviations within treatments divided by the degrees of freedom within treatments. And in this case, is 1.33. To test our hypothesis, we'll calculate the F ratio, which is the mean square between treatments divided by the mean square within treatments. Get a value of 11.28. To test the effect size, we'll calculate eta squared, which is the sum of squared deviations between treatments divided by the sum of squared deviations total. This value describes the percentage of variance accounted for by the treatment effect, and in this case will be 65.2%. Now we'll use our F ratio to test our hypothesis, but first we have to determine our critical region. So the numerator for our F ratio is the degrees of freedom between treatments, which is our total number of treatments minus 1. In this case is 2. The denominator of our F ratio is the degrees of freedom within treatments. In this case, it's 12. And so we'll move our sliders for our numerator and denominator to the appropriate places of 2 and 12. We'll select a one-tailed test, and since we have an alpha level of 0.05, we'll have 95% in our body and 5% in the tail. When we move our slider to the appropriate place, we see we have a critical F of 3.885. We can see that our F value is in the far tail in this diagram, so we will reject the null and conclude that the treatment conditions significantly affected the result. You can also find the critical F value by looking in the text in Appendix B, Table B4, the F distribution, and crossing the numerator and denominator, and you'll come up with the same value. We describe our findings by saying the analysis of variance showed significant mean differences among the three treatments. F of 212 equals 11.278, P is less than 0.05, and eta squared equals 0.652. So our next example is the long road to eta squared, where we're given a raw data table. And first we're going to complete the summary table, and we're going to start with our sum of squared deviations. But to find those, we need to calculate our sum of x and sum of x squared values. For the sum of x, you'll add up all of the scores for each treatment, or in this case, population. And then we'll find the square of each score and add them all up to find the sum of squares. To find the mean, we will take the sum of each x and divide it by n. Since these are all 10 scores each, all we have to do is move a decimal over. Next, we'll fill in our t values, which is the same value that we came up with for the sum of x. Now we'll calculate the sum of squared deviations for each treatment individually, and we'll mark them with a subscript to identify each one. The sum of squared deviations formula is the sum of x squared minus the sum of x squared divided by n. And in this case is 0.7852. We'll calculate the second sum of squared deviations the same as the first and come up with 0.8081. And our third is 0.645. Our capital N value will be the total number of participants in the whole study, which will be the sum of each of our treatments or populations. In this case is 30. G is the sum of our t values, and in this case is 101.71. To find our grand total sum of x squared, we'll take each sum of x squared and add them together to find our sum of x squared. And in this case is 349.487. Now that we've completed our summary table, we can move on to the ANOVA table. First we'll find the sum of squares within treatments, and we add the sum of squares from our first group to our sum of squares from our second group and the sum of squares in our third group. We come up with a value of 2.238. Next we'll find our sum of squares total with our grand total sum of x squared of 349.487 and subtract g squared divided by capital N and come up with a value of 4.656. Using these two, we can calculate sum of squares between by taking the sum of squares total and subtracting the sum of squares within. This way, we come up with a total of 4.656 minus 2.238, which equals 2.418. Our degrees of freedom between will be our number of treatment conditions minus 1, which is 3 minus 1, which is 2. Our degrees of freedom within is the sum of the degrees of freedom of each condition. So in this case, we have 9 times 3, which is 27. Now we'll calculate our mean square between, which is our sum of squares between divided by the degrees of freedom between. In this case is 2.418 divided by 2, which equals 1.209. Our mean square within is our SS within divided by the degrees of freedom within, which is 2.238 divided by 27, which is 0.083. And we'll use these mean squares to calculate our F value, which is the mean square between treatments divided by the mean square within treatments. And we come up with an F value of 14.57. To determine whether this value is significant, we will find our critical F with our numerator of 2 and the denominator of 27, setting our alpha level of 0.05 in a one-tailed test. Since our F value of 14.57 is in the far tail of our critical region, we'll reject the null and assume that there is a significant effect. Next, we'll calculate eta squared and determine the percentage of a variance accounted for by the treatment effect by dividing SS between by SS total and come up with 519 or 51.9%. And that's it for today. I hope this video helps you calculate your Chapter 12 End of Chapter questions. And hopefully you're getting started early because you've realized that they're going to be fairly lengthy calculations. See you next session. Take care. Good luck.